Yeah, okay, thank you. Alright, good afternoon everyone. So yeah, let's resume the perfect matching polytope, solid bricks, etc. Right? So let's do a quick recap since it has been a while, I guess. Right, so solid matching chord graphs or solid graphs are those matching chord graphs in which every separating cut is a tight cut. So clearly bipartite graphs are a subset of solid graphs. Right? And it's a proper subset. We have seen examples already in the difference. And one of the things you've already noted is that a matching chord graph is solid if and only if each of its bricks is solid. And let's also talk about this decision problem. DP solid, I guess. Given a matching chord graph, decide whether it is solid. Right, and because we can compute the bricks and braces in polytime, because of this, it follows that it suffices to solve this problem for bricks. So given a brick, decide whether it is solid. Okay. So that is an open problem in the sense that it is clearly in co-NP, but it is not known to be NP and therefore also not known to be NP. Yeah. Okay. And let's relate all of this stuff to the perfect matching polytope, right? So we have seen Edmond's theorem, which says that, so we are restricting ourselves to matching chord graphs now. So the perfect matching polytope of a matching chord graph is simply the set of solutions to this system, non-negativity, degree, and the so-called odd cut constraints. Yeah, for every non-trivial odd cut, the sum across that cut should be at least 1. Yeah, and we consider two relaxations of this. One is a fairly famous fractional perfect matching polytope where you just throw away Edmond's constraints, right? And that's very well studied. And the other relaxation we are going to consider that falls between these two. So note that the perfect matching polytope is clearly a subset of the fractional perfect matching polytope for a given matching chord graph G. However, we can also look at one intermediate relaxation, which is a set of all solutions to non-negativity and tight cut constraints. Right? For each tight cut, x across that cut has to be equal to 1. Right? And observe that this fellow is actually sandwiched between these two. Well, this is clear. This is basically, I believe, 7.4. Yeah. All right. So of course this leads to some interesting questions. When do these things hold with equality? Right? And I actually want to make one correction based on Santosh's remark last time. The way I defined Birkhoff von Neumann is actually very strange, so I want to actually change the definition because the original definition, the reason we call it Birkhoff von Neumann is not because of the way I defined it. So, what is known due to independent results of Birkhoff and of von Neumann is that for bipartite graphs, these two are equal and therefore all three are equal. This is due to results of Birkhoff and von Neumann from the 50s or 60s. However, it turns out that even in the context of matching chord graphs, there are more graphs that satisfy this equality. So those are what we call the Birkhoff von Neumann graphs. Now, of course, the definition I gave earlier is equivalent because of the theorem that one of the things you'll be proving on your assignment. So Birkhoff von Neumann graphs, the definition I would like to use is actually this. It is those matching chord graphs for which the perfect matching polytope is equal to the fractional perfect matching polytope. Right? Those matching chord graphs for which these are equal. Yeah. So that's how we'll define it actually. And the thing that we were trying to prove, I actually forgot to mention this theorem 7.8 star that we were proving last time and we did not finish it, is actually due to Balas, 1981. It says that a matching covered graph is not Birkhoff von Neumann if and only if it has a conformal odd bicycle. This is what we were trying to prove last time and we did not yet finish it. Okay? Yeah. In fact, there is an interesting story behind how I got to learn about Balas's result that maybe I will try to share with you. So, one of the first papers I read as a PhD student was CLM 2004. That actually, I think the title is The Perfect Matching Polytope and Solid Bricks. If I'm not mistaken, that's the title. Okay. And there are a couple of results. It's a very short paper. It's one of the shortest papers CLM have ever written, I think. Like 4 or 5 pages. It was a paper I actually presented as part of there was in the PhD program, there was a requirement of some course you had to do where you had to sit through some talks and then you had to actually give talks. Right? And as part of that, I presented this paper. So it was like one of the first technical papers I ever read in matching theory. And one of the results in that paper was the same thing for bricks. Yeah. A brick is, they don't use the word Birkhoff or Neumann. They say a brick is not solid if and only if it is a conformal odd bicycle. They also don't use this term. They just say 2 cycles, blah 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 blah. Right. And it was much later that I was working on, I think it was much later in my PhD or maybe in my postdoc years that I learned that this result was not only true for bricks, it is actually true for all matching covered graphs if you define things the right way. So this is actually a generalization of that result that was there in CLM 2004, but they were not aware of Balas's result. So that is why they proved that result only for bricks, but actually if you can just use 1981 result of Balas, it's actually an immediate corollary because this is for all matching covered graphs. There were more results in that paper, but yeah, in some sense, later we found out that some of it was just subsumed by Balas's result. And in fact, the person who actually told me about Balas's result, I think is my friend Cedric, who is my standard go-to person for combinatorial optimization queries, one of my go-to people. Anyways, so Cedric is the one who told me that, hey, this is more generally true. Why are you going on about bricks? So, yeah. Okay, cool. Alright, so let's look at the proof. I do believe that the term Birkhoff von Neumann for this class is probably due to my paper with CKWL, so with Carvalho, Wang and Lin. This was published in 2020 and I think one of my main contributions was coming up with a fancy name Birkhoff von Neumann, because that sells. Solid doesn't sell. It's not solid enough. Right.
You said this 7.8 star is a corollary of whatever Balas proved, but do you remember what the statement?
Oh no, yeah, so 7.8 star, actually Balas's result applies to all matchable graphs. So in fact you can go to the proof and you can see that we will actually never use even the matching covered property. But then I have to define Birkhoff von Neumann for matchable graphs, which I don't want to do because I generally use it for only matching covered graphs. So actually the whole thing will go through for matchable graphs, graphs that have a perfect matching. Yeah, yeah. I've never read the whole of Balas's work. It's written in a very different language, so I tried to read parts of it, but it was really not easy for me. Yeah. Okay. Any other questions, concerns? So we have seen one direction. One direction was quite easy. If there is a conformal odd bicycle, you just put half, half, half on those two cycles' edges, and you put one on the perfect matching outside because of conformality, and observe that this vector satisfies non-negative integrity constraints, and because the odd cycle, the cut of any of those odd cycles, you're not using any edges, the x of the partial of that cut is 0. Therefore, it doesn't satisfy Edmonds constraints. So therefore, the vector does not belong to the perfect matching polytope. Right? Therefore, we are done with that direction. So if there is a conformal odd bicycle, then we are done. This is relatively easy. Yeah. Now we look at the other direction. So now let's suppose you have a matching code graph that is not Birkhoff or Neumann. Well, that means that this is a proper subset of this. So let's say G is a matching covered graph that is not Birkhoff or Neumann. So by definition, the perfect matching polytope is a proper subset of the fractional perfect matching polytope. Therefore, there is a point here that is not here, but we can use a stronger version. There is an extreme point of this fellow that is not here. Because if all extreme points are here, well then the whole thing is here. Right? Which implies that the fractional perfect matching polytope has an extreme point x, say, that is not in the polytope itself, the perfect matching polytope itself. And at this point, well, we can't do much unless we have a good understanding of extreme points of the fractional perfect matching polytope. So that is one of your exercises in assignment 2, which we just stated last time, theorem 7.7. I'll just give a visual description instead of writing down the whole statement. So it's a characterization of extreme points of the fractional perfect matching polytope. And basically what it says is that you take any extreme point, you look at its support, it's just going to be a bunch of odd cycles and a bunch of K2s. And now it's not easy to deduce further that the K2s will have 1s and the odd cycles, all edges will have halves. There is no other way to complete things, right? So I'll just give an example. Basically, every extreme point just looks like this. These are odd cycles. Maybe I'll just put 3, 5, 3, 3. All of these are half, and of course these are just K2s, so they are 1s. That's it. Every extreme point looks like this. Right, and that's on your assignment assignment 3. It's not difficult to prove. Lucchesi-Murty have actually broken it down into smaller parts, and that makes it significantly easier. Give it a shot. So we'll use this. So we have an extreme point that is not in the perfect matching polytope, extreme point of the fractional perfect matching polytope. Therefore, it has to look like this, and in particular, because it is not in the perfect matching polytope, there have to be at least 2 odd cycles and an even number of odd cycles in the support of this graph. By theorem 7.7, and since x is not in the perfect matching polytope of G, the graph induced by the support of x has at least 2 and an even number of odd cycle components. You agree? And observe that if I take all the odd cycles of this graph, that is an even number of odd cycles, pairwise vertex disjoint, and together that is a conformal subgraph, because outside you have K2s, right? So say C1, C2 up to CR, where R is at least 2 and R is even. Clearly, this whole thing viewed as a subgraph is conformal. If R is equal to 2, we are done. By definition, that's a conformal odd bicycle. Yeah. So the whole game is to show that R can be chosen to be equal to 2. So, well, there are multiple ways to finish it. You can do it algorithmically. You can, supposing there is 4 cycles, now see if you can reduce the number of cycles to 2. If there is 6 cycles, reduce to 4, then reduce to 2. Well, alternatively, I can just choose such a family with R minimum at least 2. Right? So, choose any such family. By such family, I mean it's a set of pairwise vertex disjoint odd cycles, and the union is conformal with R at least 2 and R as small as possible. Claim R equals to. If you prove this claim, we are done. So let's suppose R is not equal to 2 for the sake of example. Let me consider R equal to 4. 4 is a nice number. So maybe I'll make them all 5 cycles. They don't have to be. Okay, let's make one of them 7 cycles. Okay. Okay, fine. 2 5 cycles, 2 7 cycles. Supposing I have 4 odd cycles, C1, C2, C3, C4. This is a support of this graph, right? We are looking at G. I mean, at this level, we don't really, at this point, I don't really care about this. All I care about, maybe I should forget this. All I care about is there is a subgraph like this. Bunch of odd cycles, vertex disjoint, and together they are conformal. And we have chosen such a thing with R as small as possible. Supposing R is not equal to 2, let's say it is 4. Let's try to reduce it to 2. At this point, DIY, and I will come around and talk to you. DIY arrive at a contradiction. To the fact that R was chosen to be as small as possible. And the hint is SGT. The original graph is matching covered. In particular, it has a perfect matching. If anyone wants a hint, let me know. I'll come and give you a hint. Okay, anybody want the hint? Anybody else? Or hint? Maybe I'll give a hint to everyone. Yeah? Here is a hint. Maybe I should write it down. People in the video might be getting bored. Hint. Consider two appropriately chosen matchings and their union. The main point is you have to choose the matchings carefully. If you choose them very carefully, then things just work out. One of them I have already kind of given it away when I emphasized that the graph G is matchable. Right, so one is clear, right? M is a perfect matching of G. That much I will do. So the pink one, M, is a perfect matching of G. This is clear. Now you need to think about what is N. The blue matching. What is N? Yeah. Even if you don't get the whole N in one shot, try to come up with some partial N. else? Any ideas about N? Right, so Shalhoub's point is N should contain these edges. Okay, so that is actually correct. I mean, that is a correct idea. N should contain all these edges. But if you just take this as N, is that good enough, or should you do something more? And maybe there are multiple N's that work. So these blue edges are there in N. Remember, this is conformal. So when I delete all the vertices, the remaining graph has a perfect matching. So Shalhoub is considering any such perfect matching, and that is her N. But is this N, or should we add more things to N? That's my point. Yeah, sorry if you have gotten, like myself, used to thinking about matchings as perfect matchings. When I wrote appropriately chosen matchings, I genuinely meant matchings, not necessarily perfect. But yes, that's a common mistake when you work on perfect matchings for a living. So I don't know if this N works, but if you add more things to N appropriately again, then it suddenly starts working. Okay, anybody else? Any ideas? Any thoughts? shot. Give it a shot. Try something. Okay, anyone else? Want me to tell you what n is? Okay, fine. Anybody else? If not, I will tell you what n is, and then you can work out the rest. Well, I'm sure there are multiple n's that work. I'm not sure. I mean, it could be, but here is one n that works. So you took these edges. Now for one of these 4 odd cycles, I will consider any maximum matching, and this is my n. This is my n, as shown. Take all the k2s outside, and for one of the odd cycles, out of the 4 or 6, whatever you have, on one of them you just make a maximum matching. Now I want you all to think about n union n, blue union pink. See if you can think about blue union pink and finish the argument. Right? Union of 2 matchings. That is something you have thought about a lot. And let me call this vertex U. Now think about blue union pink and see if you can finish the argument. And my suggestion is, there's no need to think algorithmically also at this point. At this point, you can simply think about union of 2 matchings. There's no algorithm when you take the union of 2 matchings. It is just a bunch of components. What will the components look like? And we are interested in the specific component. That specific component, what does that look like? Okay, if you have figured it out, let me know. Right now, you just have to look at blue union pink. There is nothing else. Consider M union N and see if you can finish the argument from here. wants a hint, let me know. Yeah. Anybody else? Want a hint? Okay. Want a hint? Okay, so the final hint is in N union N, blue union pink. Just consider the blue union pink graph, right? So standard STT stuff. Well, it's a spanning graph because M is a perfect matching. So therefore, whatever graph you have, M union N, it's a spanning subgraph. So the vertex U belongs to some component. Analyze this component and try to finish the proof from here. Right? U is blue exposed. It is blue exposed, and of course it is M covered because M is a perfect match. Right? So now think about the path. Well, it will be a path, right? M union N is a graph where every vertex has degree 1 or 2. Degree 0 is not possible because one of them is a perfect matching. So every vertex has degree 1 or 2. Therefore, the components of this M union N subgraph are paths or cycles. Yeah? And in particular, the vertex U is a degree 1 vertex. I have no idea where the pink edge goes. Pink edge could be in the cycle. The pink edge incident at U, it could be in the cycle, it could be going out, I have no clue. What I know is that there is no blue edge and there is a pink edge. Therefore, its degree is 1. Therefore, U belongs to a path in N union N. Consider that path. Let's write down. Maybe I should. Maybe I'll erase theorem 7.7. Now it doesn't matter. Of course, it was crucial for our proof. Let P be the path of M union N. Let me call it path component. It is clearly a path component or a component isomorphic to a path that contains U. Yeah? And it starts at a pink edge. Where should it end? The other end of this path. What color should it end at? Can it end at a pink edge? Should it end at a blue edge? What should it end at? It has to end at a pink edge, right? Because if you end at a blue edge, well then that vertex, because pink is a perfect matching, right? And everybody else is already matched because that's how paths will look like, right? That has to again be extended, right? So therefore, when you look at the other end, it will also be, basically the path will look like this. It will start at pink, end at pink. That's what the path looks like. Yeah, this is simply the path of n union n that contains u. So therefore it starts at u because it's a degree 1 vertex. This is blue exposed, and this will also be blue exposed, which is why it is a path. Right? It's a component. So where is this creature? Let's call this V. This is a path of odd length. Clearly u is not equal to V. It's a path of odd length. Right? And so where is V? V has to be a blue exposed vertex. Well, the only exposed vertices, we know all the exposed vertices for blue. It has to be in one of the odd cycles, right? Because the only exposed vertices are u and the vertices of all the other odd cycles. So I might as well assume without loss of generality that V is here in this odd cycle, the second last odd cycle, why not? Yeah, by relabeling. So I have a path in, this is the same path, right? The path P is a pink blue path that starts at U. I don't know what else it does in life, but it ends at V, right? But all the vertices of this path except for U and V are n saturated. N saturated. Therefore, the entire path has to live in the vertices that are n saturated. Right? The path cannot go to these vertices. Right? The only unsaturated vertices, n unsaturated vertices or exposed vertices of this path are U and V. So therefore, whatever this path looks like, it basically just moves around here in this part of the graph. Let me color this part of the graph. This path lives in this part of the graph. It cannot use any vertices outside of this orange stuff. You all agree? And it's an augmenting path with respect to the blue matching. It is an n augmenting path. So therefore, when I take the symmetric difference of n on this path P, consider n symmetric difference P. It will be a perfect matching of this graph, of the orange graph. You all agree? Because the blue edges are saturating all the vertices except U and V. Therefore, when I take the symmetric difference augmenting path, I have a matching that saturates two more vertices. Well, therefore, it saturates all the vertices in the orange graph that I have drawn. Right? This is a perfect matching of the orange induced subgraph. Yeah? Whatever vertices are in my orange stuff. Yeah? So I have a perfect matching here. Well, now I can make it a perfect matching of all of this stuff. And now I have reduced my number of odd cycles by 2. If it looks like cheating, it's fine. Revisit the arguments and convince yourself that there was no cheating. Yeah. So therefore, R should have been 2. If it is anything more than 2, we are able to reduce it by 2. But we chose R to be as small as possible and at least 2. So it was equal to 2. So that's it. Whatever, somewhere I finished the proof, I don't know. Okay, whatever. Yeah. Alright, so that was that. Maybe we can take a very short break. I need to finish today a bit earlier. Maybe by 6:45 I should finish. So yeah, let's take a 5-minute break and then let's resume. Yeah, but let's not make it longer than 5 minutes because I need to probably finish by 6:45. What are the plans? Yeah. Okay, we must stop recording for this part. Thank you. Are there any questions or concerns regarding this proof? If not, we'll think about it for 5 minutes and see if you are convinced or not.